Okay, so thanks very much for the invitation and the opportunity to speak here. It's a great pleasure for me. Unfortunately, I can't come tomorrow afternoon to the Epsilon Deltas because I have to get home and take my kid to school. But anyway, so I thought I would tell you about some recent work with Jean-Bergan. So let's see if this works. Take two. Okay. So here are 4 different problems. There we go. No? That's the back button. That's why. Up is not forward. Up is back. Okay. So I want to tell you about 4 different problems. One is a quite recent problem of Kurt McMullen's called Arithmetic Chaos, the classical arithmetic chaos conjecture, if you like. Another one is a problem about 10 years old by LMV, Einsiedler, Linda, Strauss, Michel, and Venkatesh. And the other 2 are from much, much earlier, a problem in numerical integration and a problem in pseudorandom numbers. And in fact, those 2 problems have for a long time been known to be one problem. Zaremba's conjecture solves both of these problems. It's still a conjecture. And what I'd like to describe today is that, in fact, all 3 or 5, if you like, of these problems are one and the same when viewed from the point of view of thin orbits. So I'd like to describe a local global conjecture, formulate a statement that in one fell swoop solves all 3 of these, assuming you could solve the conjecture, which we can't. Nevertheless, partial progress on this conjecture sometimes has an effect on these problems. So McMullen's conjecture we really can't say anything about at this time. Zaremba's conjecture a few years ago we gave a solution in density to. I'll review that. And ELMV we solved this year. So underlying all of this is that picture, which I won't say anything about, but that's where the philosophy to think about these problems in this way is coming from, for those of you that are familiar with it. Okay, so let me tell you about pseudorandom numbers and the problem that was around a long, long time ago in this industry. What? My wife made me do this Prezi thing. Okay. So what's the linear congruential method? Even if you don't know what it is, you know what it is. All you do is you take a number, you multiply by something, you add something, you reduce mod something. And when you do this over and over again, you get a sequence that looks random. So let me just show you. For simplicity, we'll take the homogeneous case, c equals 0, and we might as well start with the seed x equals 1, in which case the iterates are just the graph of the map n goes to b to the n mod d. So what does that look like? Well, so to get a period as long as possible, I want to take d to be a prime and b to be a primitive root. Never mind if that bothers you. But so here's an example. Please verify that 10,037 is indeed a prime number, and that 4217 generates the multiplicative group, z mod dz. And here's the map of this graph. So it really does look random, right? So you start, here is, where are we? 4217. So when n is equal to 1, there's 4217. And then it does something really wild. And right there, that dot is Fermat's little theorem. You have to end at 1. But otherwise, it looks good and random, right? So here's another example just to make sure it's a robust. So I'm using the same exact prime, but a different root, 4015 instead of 42 whatever. And again, the map is nice and random. Again, we have Fermat's little theorem. Any questions on these 2 pictures? So the map is random. So what does random mean? Given b to the n mod d, if I give you the y coordinate, can you guess what the n coordinate is? Well, that amounts to solving the discrete log, which this is why you can use a credit card online. So that's a hard problem, and these maps are random. How random? How random are they really? So, okay, we can look with our eyes, but the most basic statistical test you might check is the serial correlation in pairs. So what does that mean? You're getting this long sequence of numbers, and the numbers are fluctuating all over the place, but what if you look at them in pairs? So if you look at the pair b to the n minus 1, b to the n mod d, and you know a long sequence of those, can you guess what b to the n plus 1 is going to look like? So plotting, so let's look at those pairs, which is basically the same thing as plotting x over d, bx over d mod 1 in the 2 torus. So here's the first example again, and there you have the graph. So that is a fantastically equidistributed grid. Keep in mind, I mean, the mesh here is d by d. So there are d squared possible, there's 100 million possible places I could have put a dot, and I only put 10,000 dots. Square root the total number. And that it looks like it was a grid, right? So let's just make sure that happens all the time. So let's look at our second example. So that would be a terrible random number generator, because if you know x, then you have a 1 in 5 chance of guessing where bx is going to be mod d. Okay, so the serial correlation of pairs immediately distinguishes these two sequences that looked really quite good on a first glance, but the serial correlation statistic, the first one passes it with flying colors, the second example fails miserably. Okay, so the problem, so example 1 is a great sequence, example 2 is terrible, and the problem in this industry was, if I give you a modulus d, how can we tell that one multiplier is good and the other multiplier is bad without drawing these pictures and looking at them, right? Is there some, and how do we produce good multipliers, good b's given a d? So any questions on, this was the problem from the 50s on pseudorandom number generation. The problem is clear-ish? Okay. We have many different types of problems to talk about, so I hope it won't jar you too much, and maybe somebody will get something out of one part and not another. Okay, so that was the linear congruential method. So now let me tell you about numerical integration. So this is again going back to the 50s. Specifically the quasi-Monte Carlo method for numerical integration. So suppose you want to integrate a function over the unit square. So what are you going to do with a computer? You're going to sample it at a bunch of points, let's say d points, and average. And there's this beautiful Koch-Mahlavka inequality that says that the error term that you encounter has a beautiful bound. So what should it depend on? Well, the function could be very wildly fluctuating. So that can be taken account with the first variation, for example. What else could happen? Well, you could just sample at a very badly distributed set of points, and then you'll get a large error. So the beautiful inequality is it's the product of these things. So it's just the first variation, the error term is bounded by the first variation of the function times the discrepancy of the set of points at which you sampled. So let me remind you what discrepancy says. So here's a random set of points, and I've taken some rectangle, axis parallel. I look at the proportion of points lying in that rectangle. That should be close to the area of the rectangle. And if it isn't, I take their difference, and I take the worst rectangle, and that's discrepancy. Okay? And so the goal in the quasi-Monte Carlo method, so just Monte Carlo integration says you sample these things uniformly, and good luck, and that's an estimate. But quasi-Monte Carlo is about minimizing this. The function is whatever it is. Typically, the function is given to you, but how can you sample it in the most efficient way possible? So by choosing these sample points in such a way as to get a smallest possible discrepancy. Okay, is that clear? So the first question you might ask is, what is the best possible discrepancy you could get? So a trivial lower bound, I should have said, if you just take a rectangle that zooms in on one point, then you always have 1 over d here, whereas the area is arbitrarily small. So discrepancy will never be better than 1 over d if you're sampling d points. Moreover, Schmidt showed that, in fact, you can't do better than log d over d. So that's an absolute lower bound over any sequence of d points in the unit square. On the other hand, an exercise in the central limit theorem says if you sample uniformly, like the Monte Carlo integration tells you to, you get root d over d. So this is much, much worse, which is why you don't want to sample uniformly. That's the purpose of the quasi-Monte Carlo integration, is to sample along low discrepancy sequences. Okay, well, the other dumbest thing you could do is just take a root d by root d grid. But then there's a little root d by a 1 by 1 over root d rectangle, it's exercise, that has no points in it. And so the discrepancy is again, so the purely rigid, the grid, has discrepancy root d over d. The purely uniform has discrepancy root d over d. And the lower bound for any possible sequence is much, much smaller than that, log d over d. And so the problem is, can we try to come up with a sequence that gives us something closer to the lowest possible discrepancy? And it would be nice if there was an efficient algorithm for it, since you want to do this on a computer. Okay? So any question on the Monte Carlo method, the quasi-Monte Carlo method?
So is the Hausdorff inequality best possible?
It's sharp in that you can come up with functions where that's exactly what's happening. But there are all kinds, so this is a huge industry. I'm just scratching the surface, obviously. But if you know some more about the function, then you can get better estimates, and different types of discrepancies will arise in L1 discrepancy. This is called D star discrepancy in the literature. But I'm just giving you one theorem. Any other questions? Okay. So as I said, these two problems are actually one problem. So let me tell you what Zaremba observed. So let me tell you his conjecture first. So the conjecture is, it's going to look like it's coming out of left field, and it sort of was coming out of left field when it was formulated. But as is often the case, if you want some very unique behavior, number theory will provide that behavior for you. So here's the conjecture. There exists some A, some absolute constant. Think of A as like 100 or something, or 10, or 1,000. You pick. There's some A, so that for any integer D you hand me, I can hand you back integer B, which is coprime to D, with the property that if you write the continued fraction, so if you write B over D as A naught plus 1 over A1 and so on, so this will always be my notation for continued fraction, that continued fraction expansion has all of its partial quotients, all of these AJs are bounded by 10 or 100 or 1,000, whatever number you give me a priori. So as stated, this is a problem that Euclid could understand the statement of, right? It's finite continued fraction expansions. These are rational numbers. It's the Euclidean algorithm. So the problem is using the Euclidean algorithm and putting numbers from 1 through 100 into these fractions, will you see every integer arising as a denominator of one of these numbers? Sounds like it has absolutely nothing to do with the previous two problems. But the reason Zaremba asked this, so any questions on the conjecture? The statement is clear? The reason Zaremba asked this is because he proved a beautiful theorem that says, suppose you have a fraction and all of its partial quotients are bounded by a constant A, as the conjecture claims you can always do for any denominator. Then, if you look at this pair, x over d, bx over d mod 1, so that was the serial correlation of pairs for the linear congruential generator, its discrepancy, which is what we want if we want to sample numerical integration, is bounded from above, not from below, as in Schmidt's best possible lower bound theorem. It's bounded from above by A times log D over D. So as long as A can be made an absolute constant, you get a best possible discrepancy. So this will be a sequence that reaches this lower bound theoretical limit of Schmidt's. And of course, it's extremely fast and easy to code, right? You're just multiplying mod D. This doesn't get faster than that. So it's an extremely efficient algorithm that will tell you how to get sequences that pass the serial correlation of pairs test in the linear congruential method, and at the same time will tell you where to sample a function if you're doing an integral. So what should we do? Let's look at these fractions. So 4217 has that continued fraction, and 4217 over 10,037 has this continued fraction, and this fraction has that continued fraction. And you notice these are all 1s and 2s. So if you think of this bound, A is like 2 here. So this is 2 over 10,000. That's a fantastic discrepancy, as opposed to 2,000 over 10,000, which is like 1 in 5. And that's exactly what we were seeing in this picture. So that's how you know if you're going to get a good discrepancy sequence or not. Take the modulus, take the multiplier, divide it by the modulus, compute the continued fraction, and if all you see is small partial quotients, then you'll be a fantastically equidistributed grid to be used for these purposes.
So, what is the number A in the Zaremba conjecture?
So the conjecture was just for an absolute constant, but he believed A equals 5 should suffice.
5?
Yeah. And in fact, you should be able to take A equals 2 if you allow a finite number of exceptions. But at the moment, he just cared about any A, because it'll give you a best possible. There are no known counterexamples. For 4, there are 3 counterexamples for A equals 4. So if you take the integer 6, then the only co-prime fractions to check are 1 over 6 and 5 over 6. 1 over 6 has continued fraction 6. 5 over 6 has continued fraction 1, 5. So it always uses digits greater than 4. So this is really basic elementary. Give this to a 9th grader or something. No, B and D have to be co-prime. Lowest terms. So let me tell you what's known about this. As I said, oh yeah, so Zaremba's conjecture solves both problems. So here's a theorem from a few years ago. We can take A equals 50. We can't solve the problem, but we can solve the problem in density. So the set of integers D up to a growing parameter N, for which there is no numerator that we would like there to be, with partial fractions bounded by 50, the set of these bad D's has cardinality little o n. So 100% of them do have numerators. We have, it's sharper than that, but I don't want to go into that since many of you have heard me talk about that too many times. I should point out that most recently my student, Xinyi Huang, based on earlier refinements by Frolenkov and Kahn, has managed to prove the same thing with A equals 5. So now with A equals 5, we have a density 1 subset of numbers for which Zaremba's conjecture is true. Okay. Any questions on Zaremba's conjecture before we move on to something completely different? So if you like this, there's more of it later. If you hated it, we're moving on. Okay. So that was Zaremba's conjecture. Let me go to the arithmetic chaos conjecture next. So as I said, this classical arithmetic chaos, not to be confused with QUE. So here's the conjecture. It's going to be a mouthful at first, and then we'll get deeper and deeper into the meaning. So I want to look at the modular surface. So G is SL2R and gamma is SL2Z. X is the unit tangent bundle of the classical upper half plane mod SL2Z. I claim there's a compact, or Kurt claims, there's a compact subset Y. So there's only one non-compact piece. There's just this cusp at infinity. So there's a compact subset Y. You cut off the cusp at some height. And you give me your favorite real quadratic field, Q adjoin root 5 or something. And the set of closed geodesics on the modular surface, which are defined over this field and are contained in this fundamental domain, so go no higher in the cusp than how you restricted me a priori, that set has positive entropy. So that's a mouthful. So let me immediately restate it into something much more classical sounding. So here's a reformulation. There exists some absolute number like 2 or 5 or 100, A, so that you give me a real quadratic field, as before, and you look at all the periodic continued fractions, A0, A1 up to AL, periodized. So periodic continued fractions are quadratic irrationals. I want to know when does it lie in the quadratic field that you gave me with all partial quotients bounded by 100. Okay, so this is some set. It has cardinality at most A to the L, and in fact it'll have cardinality much less than that. But the claim is it has cardinality at least some constant to the L, some constant depending on the field to the L. So that's the positive entropy is just the exponential growth of this set. Okay, so hopefully this statement is completely clear even if this one isn't. So let me tell you why they're one and the same. So what's the equivalence? So here is a picture of a closed geodesic on the modular surface. It took me a week to figure out how to draw this thing. So you're seeing it both folded up and in the universal cover, just what happens to a sample starting point in the upper half plane. So it just follows a geodesic path. It's a circle orthogonal to the real line. And the two quadratic irrationals are this number alpha in Q adjoin root 5 and its Galois conjugate. And if you move it back into the fundamental domain, it does something. You just follow the geodesic flow. You're always moving along circles orthogonal to the boundary. And when you disappear there, you reappear there, and so on. And then you close back up to where you started. That's a closed geodesic on the modular surface. Now, it's a fact that the geodesic flow codes the continued fraction expansion of the visual limit point. So let me go back so we can see this a little better. So this number, you can work out, has continued fraction 1, 2, 1, 3. So let's watch. So this is 3, 1, 2, 3, and this is 1, and this is 1, 2, and that's 1. And then we come back to the beginning. 1, 2, 3, and that's 1, and then 1, 2, and back to 1. So it's just reading. If you follow the sequence as the geodesic flow moves from one copy of the fundamental domain to another, you can literally read off the continued fraction of this visual limit point, alpha, the point at infinity, the point that you see at infinity if you go all the way out. And what does that mean? Well, what are closed geodesics? They're periodic orbits of the geodesic flow, which means their limit points have periodic continued fraction expansions. And what are numbers with periodic continued fractions? These are quadratic irrationals. Okay? So to be defined over, a closed geodesic is defined over a number field if its visual limit point, or any image of it under SL2Z, which doesn't change what number field you lie in, lies in the number field you gave me a priori. Okay? And what does it mean to have small partial quotients? You see, if I had a 2,000 there, then we would have to go left 2,000 times, which really means we have to start all the way over here and go left, 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 1,000 times until we come back down. So we would have to go very high in the cusp. So not entering the cusp is equivalent to having small partial quotients. And that's the reformulation of these two problems. And the difficulty, of course, is there's dynamics that tells you what happens to the geodesic flow. There's algebra that tells you arithmetic that tells you the number fields. And it's very hard to control these two things simultaneously. Okay? So again, there's the conjecture. There's a compact subset. There's some height at which you can cut the modular surface so that for any real quadratic field, the set of closed geodesics defined over it that don't go higher than that point in the cusp has positive entropy, has exponential growth. Any questions on arithmetic chaos? So I know that these problems are quite different from one another, and I hope that's okay, and you can hang on, because in the end, they'll all be the same problem. That's what I'm hoping to convince you of. Question?
So why doesn't it depend on D? The compact set doesn't depend on
It should be independent of D. Even if you let it depend on D, it's not known that there's exponential growth. But it should be absolutely uniform. In fact, it should be imaginary part equals 3, as I hope to convince you. Any other questions? Okay, so let me tell you the last problem. This ELMV problem, so what were they thinking about? So it'll sound a little similar to the McMullen problem. The claim is, again, there exists some compact subset of the modular surface so that it contains infinitely many closed geodesics which are fundamental. So now I have to tell you what fundamental means. So there's a closed geodesic. We already know, we discussed closed geodesics. Fundamentality isn't something that's natural to closed geodesics, but it's very natural to binary quadratic forms, and or equivalence classes of binary quadratic forms. So here's a binary quadratic form, ax squared plus bxy plus cy squared, which I'll write as bracket abc, up to equivalence. So if you make a GL2 change of variables in the x's and y's, you get the same class, and you get the same discriminant, which you know from high school, b squared minus 4ac. Middle school, some of you. The German system's better, right? And so what does it mean for a class to be fundamental? It's fundamental if its discriminant is a fundamental discriminant. So if you don't know what that means, just think of it as being a square-free number. It's essentially the same thing. So then what it means is that it's the discriminant of a real quadratic field. Q adjoint root D. Just if you don't know what it is, just it means it's square-free. These happen to be very special. And so how do you go between closed geodesics and equivalence classes of binary quadratic forms? Well, there's an intermediate step, which is that closed geodesics correspond to hyperbolic matrices. Let's see, let's zoom in here. So, or conjugacy classes of hyperbolic matrices. So this is an integer matrix with determinant 1, AD minus BC is 1. And you can check, it's an easy computation, that it fixes, because it's hyperbolic, it's going to fix 2 points on the boundary, on the real line. those 2 points are given in terms of the entries as a minus d, give or take, root trace squared minus 4 over 2c. Some simple computation. If you work in dynamics on the modular surface, you know this just like minus b plus or minus root b squared minus 4ac over. Okay. So it has these 2 fixed points. So we just, given a matrix, you just look at the 2 fixed points, then you draw them, then you draw the geodesic connecting them, and then you fold it up, and there's your closed geodesic. And they're quadratic irrationals, so they're periodic, so the geodesic is closed. How do you go from this point to a binary quadratic form? Well, binary quadratic form has these roots that you know from high school or middle school. And so you just read off, given this number, you just read off what the coefficients of the binary quadratic form are. It's completely elementary. To go in the other direction is not entirely elementary because you see here you have a minus d, and here you have trace squared minus 4, and it has to match the discriminant. There's a Pellian equation to solve. It's slightly tricky, but in fact I claim it's not tricky at all. So here's an easy fact. You probably can't see this in the back, right? It's too small. So I'll zoom in a second. But if you take the continued fractions of this number and just stick them into matrices that form A0, 1, 1, 0, A1, 1, 1, 0, and so on, AL, 1, 1, 0, and multiply that matrix out, that matrix, it's an easy computation, that matrix will fix this real quadratic. And so let me just show you with an example. So let's take these 1, 2, 1, 3 and stick them into 1, 2, 1, 3. You multiply this out. Even I can, with pen and paper, do that. You get this matrix, and that's exactly the matrix, the hyperbolic matrix I used in making this geodesic. Okay, so now we know the equivalence between closed geodesics and binary quadratic forms. We know what it means for a binary quadratic form to be fundamental, and so we know what it means for a closed geodesic to be fundamental. And so now we understand the statement of ELMV. Are there infinitely many fundamental low-lying closed geodesics? Okay. Any questions on that statement? Let me try to explain some of the motivation behind why you would ask such a thing. And to do that, let me remind you of Duke's theorem. So let's take C sub d to be the inequivalent classes of binary forms of discriminant D, quadratic forms. And if D is a fundamental discriminant, oh boy, is a fundamental discriminant, then you're just staring at the ideal class group of the corresponding field. So these are very important objects which will have no role in what we're doing. So let HD be the class number. It's finite. It's Gauss's one of his many famous theorems. And let's look at the closed geodesics, but not one by one. Let's look at them grouped by the class group. So there's not a natural way to just stare at a closed geodesic and group it by a class group, whereas with binary quadratic forms, it's extremely natural to group them by discriminant. So you go from these closed geodesics to binary quadratic forms and see what you get. So let me give you one example. So here's a discriminant 1337, which is square free, and so it's a fundamental discriminant. The class number is 1, and it's represented by the class 19x squared minus 27xy minus 8y squared. And here's the quadratic irrational, and here's its continued fraction in that picture. And here's the corresponding closed geodesic. So you see, I don't know if you saw there are these 17s and 35s and 8s and 5s, and so you can see that in the picture. So 35 is going to take you all the way up here and all the way back down, and here's a 17, and here's an 8 and a 5 and so on. So it's, again, reading the continued fraction as it follows its trajectory. Let me show you another example. So 1365 is again square free, so it's a fundamental discriminant. Now the class number is 4, and here are the periodic, here are the continued fractions of the corresponding fixed points corresponding to the 4 quadratic forms, or classes thereof. One has a 35 in it, one has a 7, one has an 11, and the other one is 1s and 2s. So they're colored blue, brown, purple, and red, if you can see. So the 1s and 2s are this guy down here, just hanging out downstairs. The 135 is this guy that just shoots up into the air and comes right back down and shoots right back up and comes right back down and shoots right back up and comes right back down. Okay? So individually, these closed geodesics are doing wildly different things. One of them just bounces up and down. One of them just hangs out downstairs. The others are in between. But if you were colorblind, those two pictures might actually look quite close. So what's Duke's theorem? You have these closed geodesics, you have this class, and you look at probability measure, which is the arc length measure on the geodesic, and you average over the class group, and as d goes to infinity, that converges to Haar measure. So that's what we were seeing back here, is that the measure is dx dy over y squared, and so the orbit spends more time downstairs than it does up here, and it's the same here, not individually, but on average over the class group. So that's this beautiful theorem that mixes arithmetic and dynamics and geometry due to Duke. Okay, so any questions on Duke's theorem?
Sorry, could you repeat the definition of d now?
It's just arc length measure. So you just integrate ds, where s is, ds squared is hyperbolic measure. So these are, so let me say, so the question that ELMV we're trying to address is to what extent do the geodesics equidistribute individually? So as we see here, if the class number is 1, then we're getting a space-filling curve. And of course, the class number is 1 infinitely often. If I could prove that, then that's what I'd be telling you instead of this. And so if the class number is 1, then there's no averaging here. There's just one geodesic. There's just one curve. And if the discriminant is very large, then that one curve is a space-filling curve. So it has to visit the cusp. It can't be low-lying. You can't give me a finite region which, for arbitrarily large d, is going to see infinitely many geodesics that don't go into the cusp. They have to go into the cusp because they have to equidistribute. And the question was really about, well, what are some of the other weak star limits? Right? This is somehow the big theme of bounded closed orbits. And so that's what you're seeing in this picture is the class number 1 case. Moreover, there's some work of Popa and Michel and Harkush and based on Losch-Berger's formula, you can actually prove that as long as the class number isn't too large, it is true that the geodesics individually equidistribute. And moreover, it's believed that as long as the class number is any epsilon power less than the largest possible, the class number can't be bigger than d to the half plus little o1. So if you have any fixed epsilon as d goes to infinity, it's believed that every single geodesic individually without averaging should equidistribute. So you should have a very hard time finding low-lying geodesics. Of course, they exist because you can just specify small partial quotients and get a low-lying geodesic. The question is, are any of these fundamental? Are only finitely many of these fundamental? So to see any non-equidistributing behavior, you need discriminants with class number as large as possible, d to the half minus little o1. So the exponent needs to go to a half as d goes to infinity. Otherwise, you're not going to, at least conjecturally, you're not going to see any such behavior. On the other hand, so here's another conjecture, which if I could say something about, I wouldn't be talking about this. The average class number for real quadratic forms should be 1. So if you sum the class numbers up to n, you should see n to the 1. The average size should be n to the epsilon. And so what does that tell you? How many of these d's can be of size d to the half up to n? There can be no more than root n of them. So it's a very sparse set of d's along which we're trying to find this very thin non-equidistributing behavior. Okay? So is that somewhat clear? So here's our theorem. You give me a constant c greater than 0, and I'll give you a compact subset of the modular surface, means some height at which I cut the fundamental domain, and a set d of fundamental discriminants. How many discriminants? Well, the number of discriminants in this set d up to n is at least n to the half minus c. You can't see, I'll zoom into it in a second. This is n to the half minus c. And moreover, for every single discriminant in this family of discriminants, the number of closed geodesics in the class, which are low-lying, which are contained in this set, and of course this class is a fundamental class because the discriminants are all fundamental, is at least the class number to the 1 minus c. So we also have an upper bound that it can't be more than class number to the 1 minus c in general, and we produce class number to the 1 minus some constant. So that's the statement. Okay. Any questions on this?
Can you reformulate it in the language of quadratic form?
So you can. So you can even reformulate it into the language of continued fractions. So this is saying you're going to take continued fractions which are bounded by some bound. Well, you give me the C first, and then I tell you what bound. And then the set of such continued fractions which correspond to binary quadratic forms which have fundamental discriminant is large. In fact, this is how, in a sense, this is how we prove this theorem. I'm just reformulating it back to the original statement. But I'll say this again after I tell you why it's the same problem as the other two.
But you will tell also how you do it.
I'll say a few words about the proof. Yeah. But the statement is clear. So you might be tempted to send C to 0 since I was putting little o1 there before. But if you send C, so the remark is you can send C to 0, but then y goes to x. So you have less and less meaning of low lying. So I prefer to interpret this as just set C equal to 1 over 100 or something. Then you have an absolute bound on the height, an absolute number like 100 that you bound the partial quotients. And you're seeing, maybe not n to the half, but you're seeing n to the 0.49 of the discriminants up to n, and you're seeing class number to the 1 minus 1 over 100 of the possible closed geodesics are low lying. So it's sharp in that sense. Okay, so any questions? Okay, so that was the ELMV problem. So so in some sense these two problems are orthogonal to each other. I just want to, this is a little philosophy. So both problems are talking about low-lying closed geodesics, but arithmetic chaos is a vertical problem where you're not changing the number field, and ELMV is a horizontal problem. So here's a picture of real quadratic fields ordered by discriminant. So here's a typical field K. And above K, there's a finite number of discriminants of inequivalent classes of binary quadratic forms whose discriminant is actually equal to the discriminant of the field. So that's these fundamental guys that you care about. And then there's still infinitely many more, but their discriminant is the fundamental one times a square. So they live in the same number field, so that it's in this tower, there are infinitely many more. And so arithmetic chaos says in each number field, I want to go up in the number field and find positive entropy of low-lying guys. Whereas ELMV, at each number field, you only have a finite number of chances to find low-lying guys. And whenever the number field has a class number that's too small, you just won't find any low-lying. So this is a horizontal problem because you have to keep changing what number field you're looking in to have a chance of finding an infinite collection. Okay? Just some. All right. Okay, and as I promised, these three problems are all one and the same. So why are they one and the same? So let me formulate our local global conjecture. So the key to this progress, as the title hints, is thin orbits. So if you remember, there was this matrix A0, 1, 1, 0, A2, A1, 1, 1, 0, and so on, and that fixes this quadratic irrational, which lies in Q adjoin, if you remember the formula, it was trace squared minus 4 was the thing under the brackets. Okay? So that was what we were discussing for arithmetic chaos. It's an easy fact that so if, again, you take the same matrix, the corresponding geodesic will be fundamental if trace squared minus 4 is square free, as you can believe. It is the discriminant. So it's not a sufficient condition, but it's a necessary condition. So that'll be for ELMV. And here's another fact. If I take the matrix A1, 1, 1, 0, A2, 1, 1, 0, up to AL, 1, 1, 0, and if I multiply all of this out and I get a top row that's D and B, that's equivalent to reading off the continued fraction of B over D. So I put a 0 there just so you're in the unit interval. So the first shift is nothing, so the number is between 0 and 1. And so all of these problems boil down to staring at matrices of this type. And all of the problems, so that was for Zaremba and pseudorandom numbers, and all of these problems are asking you to limit the size of the partial quotients of these A's. So what's the most natural thing to do? Let's define gamma sub A to be the semigroup, so I won't take any inverses. I'm only allowed these matrices and no others, generated by matrices of the form A110, where A runs up to this capital A, which is like 100. Okay? So this is a semigroup. It's a subset of GL2 or SL2 if you just take even words. And I claim it's thin. So what does thin mean? I'll give you a definition by example. So what does thin mean? So it naturally sits inside SL2 if you take even words in the generators so that you have determinant 1. And what do I mean by it naturally sits inside? It's the Zariski closure. And in SL2Z, it's been known for a very long time that the Archimedean count in a ball, so if you take an Archimedean ball of size n, the number of points you'll see in SL2Z is around n squared. And it's been known also for quite some time due to Hensley that the number of points in this semigroup in a ball is n to the 2 delta A. So what is delta A? It's the Hausdorff dimension of the limit set of this semigroup, by which I mean, so let's take the Cantor set of all numbers in the unit interval with partial quotients bounded by A. So here's a picture of this semigroup when A equals 2. So the numbers between a half and 1 all have their first partial quotient equal to 1. And the numbers between a half and a third have a first partial quotient equal to 2. And the numbers between 0 and a third all have their first partial quotient that's larger than 2. And so all of those numbers are removed. So the circles correspond to, the diameters of these circles are intervals that are being removed. And you should think of this Cantor set as you come down from the upper half plane until you reach the ground. And if you can reach the ground, then you're in the Cantor set. Okay? So this is some very natural, very long studied Cantor set. And it has some Hausdorff dimension. And that Hausdorff dimension for any finite A is strictly less than 1. But the number of points that we had in our semigroup was n to twice delta, so it's an exponent that's strictly less than 2, as opposed to the Zariski closure, which the number of points you see there is n squared. So it has 0 density points, and that is definition by example. So in general, you give me a sequence, a set of integers in Zn, I look at the Zariski closure, that's some algebraic variety. I take the integer points of that algebraic variety, and I look at my favorite Archimedean ball, and I see if the set of points in my set has 0 density in the set of integer points in the ambient algebrogeometric closure. And if it does, then I call my set thin. So that's why I'm going to call this set, this semigroup gamma A, thin. So here's a fact. The dimension of this Cantor set, this one here, has been studied for 80 years or something. It's known to 50 decimal places, and I'll spare you 47 of them, something like 0.53. And Hensley proved 20 years ago the asymptotic formula. So as A gets larger and larger, the dimensions, these Cantor sets get fuller and fuller, and the dimensions approach 1. And here's the rate. So zeta of 2 makes a nice appearance. OK. So that's this semigroup. Any questions on the semigroup or why you would care about studying this semigroup? I hope I've motivated that. So now that we see the semigroup, so what's our conjecture? So if you look at arithmetic chaos and ELMV, they're both asking about trace squared minus 4. So in particular, they care about the trace. So you want to take matrices and send them to A plus D. As opposed to Zaremba, where you want to look at the denominators, these Ds, which are the 1-1 entries of the matrices that come out in this semigroup. So then you want the first entry. A, B, C, D gets mapped to A. So more generally, if you take F to be any affine linear, it's not so important, the affine part isn't important, but the linear part is very important. It would be false if we took any higher order polynomial. So we want a linear map, which is integral on SL2Z. And what we claim is that the image under this linear map of our semigroup satisfies a local to global principle. So what does that mean? We'll call an integer n admissible if it satisfies all the local obstructions. So you want to know if an integer lies in the image, and it can't possibly lie in the image if it doesn't lie in the image reduced mod q for some q. So a number is admissible if it passes all of these local obstructions. Now it turns out that that's a very easy condition to check precisely because of the matrix interpretation. in particular, because this semigroup is Zariski dense, we have strong approximation. The reduction mod Q, in fact, is all of SL2 Z mod QZ. So for these particular problems, there won't be any local obstructions. Every integer is admissible. Every number is a trace of a matrix. Every number arises in SL2Z as the first entry. So these are the local obstructions, and they're easy to check because of strong approximation. If a number is admissible, then what should its multiplicity be? So what does multiplicity mean? It's just how many matrices are there in this semigroup whose image under this linear map is the number that you want, right? That's what multiplicity means. So what's the multiplicity? Well, if the multiplicity is non-zero, then the number appears. And in fact, not only do we want the multiplicity to be non-zero, we want the multiplicity to be as large as it should be. So how large should it be? The total number of points that we had in our ball is n to the twice the dimension. And they're not getting spread out because f is a linear map. They're not getting spread out by more than a constant. So you would expect n to the twice dimension, that's the total number of points, over n, because there are n integers up to n. So if each one is hit roughly the same number of times, then that should be its multiplicity. And let's give ourselves a little o1 to be safe, because the singular series can drop us by an epsilon. That's the conjecture. Okay? You give me affine linear map and this semigroup. The dimension is greater than a half. I should have pointed out, even for a equals 2, you saw the dimension was 0.53, which is greater than a half. So twice the dimension minus 1, this is a positive exponent. And because it's positive, and n is going to infinity, the multiplicity is eventually non-zero, which means, so these are the two Archimedean restrictions, that n has to be sufficiently large and the dimension has to be greater than a half. And then these are the finite local obstructions. And if you put them together, this is the local global conjecture. Okay. Any questions on the local global conjecture? So I'm not going to have time to tell you anything very much about it, but let me just give you a few hints as to what we did to solve the ELMV problem, coming back to your question. So what we really prove is that for all A sufficiently large, the number of matrices in this semigroup in an Archimedean ball of size n, for which the trace squared minus 4 is square free, that guarantees us that we're talking about fundamental geodesics. The number of these, if I didn't have this condition, is n to the twice the dimension, and when you add this square free condition, you don't lose more than epsilon. So that's what we really prove, and then when you unravel the formalism, you recover the theorem I stated before. So what are some of the ingredients? So of course we're going to sieve. We need to sieve down the square frees. That's an epsilon sieve, so we really don't need very much. We need a main term and an error term. The main term will come from additive combinatorics, sum product, expanders. There's a picture of an expander. And because we're dealing with semigroups instead of groups, I was spoon-fed automorphic forms and representations. This is how you count. If you have a semigroup, all that theory goes out the window. Okay, so you switch to thermodynamics, to Rel transfer operators, and congruence versions thereof developed by Bergan, Gambert, Sarnak. So that will give us a nice main term. And the issue is then, can we deal with the error term? And as stated, we can't, because we need to develop bilinear forms. And even when we develop the bilinear forms, we don't get enough from the spectral gap that one gets from sum product type things. You do not get a sufficiently good spectral gap which can handle the errors. And so what you need to do is go beyond expansion. So you need to produce a level of distribution that's stronger than what you get from expansion alone. So the beauty of expansion is it's kind of like a positive entropy statement. If you have expansion, then you can sieve, but you can't quite sieve far enough in this application. And so we need to produce a level of distribution that's stronger than the one you get individually. And in fact, this aspect of the work is very similar to what you're going to hear in the next lecture. Of course, it's much easier in this setting. Okay, so any question? I know I didn't tell you anything beyond words. You just have to read the paper. Chantal? Yes, I would expect not to have this little o. Yeah. And if we had the conjecture, then that's exactly what we would have. If we had the conjecture, then I could replace this little o by greater than. But since we don't have the conjecture, all we need is to sieve down the square frees. In McMullen's problem, it's much harder because you need to solve a Pell equation. So you really need to know that every single guy is there and with the right multiplicity.
So you would need not to do anything.
You need to, yeah, you need something much sharper. This is still an average result. So it's the fact that it's a horizontal problem that actually helps us. The vertical problem is much harder from this point of view. Okay, I'm out of time, so let me just say again how much this picture, working on this picture, influenced our thoughts. And so here's just some, so this paper is now on archive, and there's some discussion here about these things because I know I'm sure I went too fast. So I'll stop there. Thanks.